Have you ever wondered how doctors can see inside our bodies with such incredible, crystal clear detail? How they can build these amazing 3D models from what used to be just a flat, shadowy picture? Well, today we're talking about the incredible technology that made all of that possible, the CT scanner. Let's dive in. So this is the big question, right? This was the challenge that really drove the pioneers in medical imaging. How could they possibly get past the limits of a regular X-ray to see the body not as a confusing shadow, but as a series of clear individual slices? This is where our story really gets started.
Okay, so before we can really appreciate the genius of the solution, we have to understand the problem. And for decades, the problem was that a standard X-ray was, well, it was just flat.
Just think of a conventional X-ray as being like a shadow. It literally takes our entire three-dimensional body and squishes it down onto a single two-dimensional film. And the biggest issue with that is something called superimposition, where all your organs, your bones, everything, it's all just stacked on top of each other in the image. This makes it incredibly hard to tell things apart, especially when you're looking at soft tissues.
So imagine a doctor sees something that looks like a tumor on an X-ray. Because of all that overlapping anatomy, it's almost impossible to know its precise location. Is it near the front of the body? Is it somewhere in the middle? Or is it way in the back? Looking at this puzzle here, you get the idea. Is it in the circle, the triangle, or the square? You just can't tell. And that ambiguity was a massive hurdle for doctors.
So yeah, clearly, a totally new way of thinking was needed. The answer wasn't to try and get a better shadow, but to stop thinking in terms of shadows altogether.
And the breakthrough came from this one core concept, tomography. The name itself is a huge clue. It comes from the Greek words for slice and to write. And that's exactly the idea, to create an image of a single cross-section of the body, just one slice, without all the confusing stuff above and below it getting in the way. This was the real game changer. By focusing on just one plane, one slice at a time, you could finally get rid of that superimposition problem. You could actually see what was really inside that slice with incredible clarity. But, figuring out how to do that, and especially how to do it fast, kicked off a kind of technological arms race. So, once the concept was there, the next huge challenge was making it practical for a hospital. This set off a super rapid evolution of CT scanners, with each new generation getting dramatically faster and way more powerful than the last. Just take a look at this timeline. It's kind of mind-blowing. The very first scanner back in 1971 took 25 to 30 minutes just to get the data for a single slice. Can you imagine? Then, just a few years later in the mid-70s, the second generation could do it in about 90 seconds. By the late 70s, the third and fourth generations got that down to just 1 or 2 seconds per slice. That's just an absolutely incredible acceleration. So how on earth did they get that much faster? Well, it all came down to a few key upgrades. The first generation, you see, used a single slow pencil beam. The machine had this clunky process where it would scan across, rotate 1 degree, scan across again, over and over. Super slow. The second gen was a bit smarter, using a wider fan beam and more detectors. But the really big leap came with generations 3 and 4. They used a really wide fan beam and hundreds of detectors that could just rotate smoothly all the way around the patient, which got rid of that clunky stop and start motion for good.
And then came the fifth generation, also called EBCT. This machine was a specialist. It was designed for one specific, incredibly difficult task, imaging the heart. See, the heart is always moving, which makes it a huge challenge. So this machine was engineered to be so ridiculously fast, we're talking images in less than 50 milliseconds, that it could effectively freeze the motion of a beating heart.
But even with these incredible speeds, scanning was still a bit of a stop-and-start process. You'd scan one slice, move the patient, scan another slice. The next great innovation would change all of that, leading to the truly three-dimensional imaging we're all familiar with today.
This comparison right here makes the difference crystal clear. The old way was this cycle. The table would stop, the machine would scan a slice, then the table would inch forward to the next spot, and you'd repeat the whole thing. Helical, or spiral CT, just threw that whole process out the window. The X-ray tube rotates continuously, while the patient's table moves smoothly and continuously through the scanner at the same time. And the result of this continuous spiral motion was, well, it was profound. Because it was so fast and so smooth, doctors could now scan an entire volume of the body, like your whole chest or your abdomen, in the time it takes for you to just hold your breath. This was a true revolution. It made scans way quicker for the patient
and created these perfect, seamless 3D models for the doctors to work with.
Now, making this leap wasn't easy. It took 3 key innovations working together. First, you needed a way to get power to the spinning part of the machine without having cables getting twisted into a giant mess. That's where slip ring technology came in. Second, all that nonstop spinning and scanning generates a ton of heat, so they had to invent much more powerful and durable X-ray tubes that could handle it. And finally, you're not getting neat individual slices anymore. You're getting a continuous spiral of data. So they needed brilliant computer algorithms that could turn that spiral back into a clear, understandable image.
So, we've talked about the theory and the history, but what's actually going on inside that big donut-shaped machine when you're in there?
So inside that donut, which is called the gantry, is all the critical hardware mounted on a frame that spins around you at high speed. You've got the X-ray tube that creates the beam, a detector array on the other side that catches the beam after it passes through you, and a special computer system that grabs all that information and converts it into digital data.
And just to give you a sense of scale, that opening that you slide through, the aperture, is typically somewhere between 70 and 90 centimeters wide. It's inside this ring that all the magic happens.
And it all comes together in this really elegant process. The table moves you at a perfectly steady pace through that opening, and as it does, the X-ray tube and the detectors are spinning rapidly around you, continuously collecting data from every possible angle to build that complete 3D picture.
So when you really step back and think about it, the progress is just breathtaking. We went from a 25-minute process to get one single grainy slice to capturing a high-resolution 3D volume of an entire organ in just a few seconds. It just makes you wonder, right? With technology moving this fast, what will the next great leap in seeing inside ourselves even look like?